Demonstration I'm going to do with PYOTE is the event detectability tool. This data file is my own. It's from 3772 PYOF that I turned in. The target star was 11.1. The telescope was 12-inch Meade LX200 GPS at f3.3, and the star altitude was 32 degrees, and it was summer skies in Arizona. Now, I mention this because I use this tool as a predictor of future events. And so if I'm going to use it, I have to base it on noise that I expect for the future event. So over time, I'm going to build a catalog of observations that are in different seasons at different altitudes, so that the noise that I use to predict if I can see a future event is going to be as similar as I can to the noise of the future event. So I want to be clear that you have to include, you have to do this over time, building up a catalog of observations that you can use to determine if future events will be visible. So my first demonstration, I'm going to show how to determine how short of an event you can detect when there is a large 5+ mag drop. My second demonstration will be from the same light curve, but to determine the minimum duration of an event with a medium range mag drop, say 1 to 2. And then the last one is going to show how to determine the minimum duration of an event with a very small mag drop, say 0.01 to 0.02. And I have given this demonstration before to a small group of North American observers, and you can see a longer presentation of this at this URL link. It's also listed on the IOTA website under PyMovie demonstrations, I believe. Whoops, I'm not going to thank you yet because I'm going to go to the next thing. Okay, so I'm going to read a new light curve, and this is the PF one. So I'll full screen this. Okay, so this is my PF light curve. It's a very good event. You can see it's a huge mag drop. I think I mentioned the mag drop. The predicted mag drop of this one was 5.1. And so I got a nice big mag drop. So there's no concern that I have an event. But say I have a future event where I'm going to have a 11.1 magnitude star at the same altitude in the same season, I'll use this as a predictor of my future event. So I'm going to go to my noise analysis and detectability tab. I'm going to set a baseline that does not include my event, because that's not noise, that's a real drop. And I'll mark that side. Then I'll go over here and mark this side. And mark that baseline. So now I've got all the baseline marked that excludes the actual event. I'm going to calculate the baseline, mean, and sigma and correlation coefficients. And it gives me a report of those down here in the text box below. So now I can say, well, if I observe for 120 seconds, which is 2 minutes, which I normally do, and say that the predicted event duration of my upcoming event is 2 seconds, or actually 1 second. I usually use 2 times the maximum event duration as a limit. So say the future event is 1 second, I'll double that to 2. And then I want to use a duration step, which is increments of 2 or less that I can use for my future prediction. And I'll usually start with 0.1, which will give me 20 steps in a 2-second event. And now my backdrop is going to be 5. So I want to see how short of an event can I detect in this typical light curve if it was a 5 mag drop. And I'll run calc detectability, and it starts a series of false positive tests. And if you'll notice in the top line, each event duration that it's looking at is 0.1 seconds less than the previous one. Now, each of these events are passing the false positive test. So if I pull this over, you see the red bar is way right of the black bar. So it just churns along here and it keeps going. And it finally quits, and it says in red text, an event duration of 0.1 seconds with a mag drop of 5.0 is likely detectable. So if my future event is, say, 0.5 seconds, then I'm saying, I'm pretty confident I can see that if it occurs, because I can see down to 0.1 seconds. Now, I may want to test that a little bit, so I can go 0.2 here as a, 0.2, and I can change this to 1/100th of a second at a time, and I can see if it can go even shorter than that. So I reached 0.1 because 0.1 was my duration step, but I may actually be able to go smaller than that. So let's look at that. So now we're at 8/100ths of a second, 7/100ths. So in fact, because I went in smaller steps, the event duration that I could really see as a minimum and still be detectable from noise, meaning it's statistically different from noise and would be a valid event if there weren't some other causes such as clouds or birds or whatever, then that would be an event duration of 0.07 seconds. So that just shows you what we can do with trying to see, well, what's the shortest possible event that I could get out of a typical event like this. Now, the next thing I want to do is, what if it wasn't a real deep event like 5 mag drop, a mag drop of 5, but something much smaller. So I'm going to guess, I should be able to see at least 5 duration seconds. And I'm going to go, instead of 0.01, I'm going to go to 0.5 because I've got more seconds. So I want to just see, I want to reduce my computation time. So now I'm looking for a mag drop of 1 mag drop. And I'll run that from 5 seconds down. And that's the plot of the simulated event. And the simulated event has an event duration of 0.5 seconds at a mag drop of 1. And you can see that it's fairly clear, and we'd likely be able to see that. Could I see something smaller than that? Well, maybe. So let me put 1 and go to a step of 0.1. So this will run 10 times. And so I could see an event with a mag drop of 1. I should be able to detect an event as short as 0.3 seconds. And that's because my simulated event has several points down here at the bottom. And it would likely be detectable with PYOTE at the 4 sigma level. Okay, so my last test here is going to be, I'm going to use the same noise, but now I'm going to say, can I see an event with a 0.1 mag drop? And I know that it's very hard to see those unless you have a very long event. So I'm going to go 10 seconds. And I'm going to do that at 0.5 of a second so it doesn't run through so many iterations. I'll press count detectability. And it stops at 9.5 seconds. So it says, yeah, there's an event there. There's your disappearance line. There's your green line. This is a simulation, but it's detectable at 9.5 seconds long. So if you had a 5-second event, maximum duration, and the mag drop was 0.1, you wouldn't be able to detect it because it's too short. The shortest event that you can statistically detect with this degree of noise in your light curve is 9.5 seconds, or around there, 9 seconds, 10 seconds, something like that. So that's how you use the event detectability tool as a tool to decide if you want to even try a future event. Now, I've been doing this quite a bit lately. I've been trying 15.2 mag stars with 3 mag drops. And this tool has been very accurate for those types of events. So I'm very happy with the way the tool has evolved and how it works. And I would encourage others to try to use it to predict future events. And if you're successful in doing that, I'd be happy if you'd share those with us so that maybe in a future presentation, we can give some actual before and after, say, this is what I predicted and this is what we actually got. So thanks for your time, and a special thanks goes to Bob Anderson, who has created this nice suite of tools that we're able to use to refine our analysis.
Thank you very much for that presentation, Tony. It seems to me that you don't actually have to have a database of actual occultations in order to do this analysis. You could go make a video of a star cluster that has stars of various magnitudes, and you could do it at various altitudes and so on, and thereby ascertain what your signal to noise ratio is over the background. And you could use that in the same way. It would work just as well. In other words, a 5 magnitude drop is basically, an over background noise. And so right. you could do the same type of calculation just by having the light curve of a star without an occultation.
Yes, and that's exactly true. But I wanted to start with a light curve with an occultation, yeah, so you know that this is real stuff,
Yeah. Yeah, sure.
All right.
Okay.
So it's not just bogus stuff, but you're exactly right. And I have done that. I've used little galactic clusters that, have a fairly nice variety of stars in the 10 to, 14 magnitude range, maybe 15, and it works out really nice.
Yeah, and this is one way we can get away from the idea of sending in reports with, about possible occultations with signal to noise ratios of 0.25. I mean,
Right.
we could, by doing this beforehand and planning our observations better, we'll get better science.
Yeah.
See what I mean?
Right. And we've actually put this into practice. So a lot of reports that Dave Harold doesn't get have been screened out by being able to show that the noise, there's so much noise in the light curve that you couldn't have detected the event that you say you're reporting.
Mhm. Yeah.
Because
And that is much appreciated.
No.
okay, so thank you guys.